The next transport and fate process we'll discuss is retardation, which happens because of adsorption of chemical to the soil. And I'll use the terms adsorption and sorption interchangeably. So the chemical sticks to the soil but comes back off. So what happens is that the chemical is slowed down in its transport. The slowdown, the retardation, can be represented by a retardation factor. That's just a ratio. So the time it would take the chemical to move through the soil with the adsorption is the retardation factor, R, times the time of a conservative chemical, or the time that we calculated previously just using Darcy's law. Or we could say that the velocity of the adsorbed chemical is 1 over R times the velocity of the conservative chemical. And it turns out we can calculate that retardation factor from the sorption properties of the chemical in the aquifer. So previously we talked about KD, the soil sorption coefficient or distribution coefficient. So the retardation factor is 1 plus rho b, the bulk density, over n, the porosity, times kd. So if kd is 0, it doesn't sorb. The retardation factor is 1. So the chemical just moves with the water. If it's anything more than 0, it's slowed down by a little bit. So we'll start off with this example here that builds off of our previous Darcy's law example. So this is the same example that we started with way back when, and now we're going to add adsorption to it. So the first thing we did is we found the head, which we'll need for Darcy's law. It's the top of casing minus the depth to water. So this is 1040.1, and this one is 1031.1. So it drops 9 feet. And the hydraulic gradient then is the 9 feet it drops over the 900-foot distance equals 0.01. Our Darcy velocity or Darcy flux, our specific discharge, all different names for the same thing, is the flow divided by area, and that equals the hydraulic conductivity times the hydraulic gradient. Really, the hydraulic gradient is negative in direction of flow, so we have a negative there. Don't get caught up with the negatives. If your water goes uphill, you got the sign wrong. And so that equals 18 feet per day times the hydraulic gradient of 0.01. And again, if we do the signs, negative and negative, that's positive. So the specific discharge is 0.18 feet per day. It's not really how fast the water is going. For that, we need to divide by the porosity. So it's 0.18 feet per day divided by the porosity of 0.24. And I kind of ran out of room there, but that's 0.75 feet per day. So the Darcy's law velocity would be 0.75 feet per day. So the time it would take is 900 feet divided by 0.75 feet per day equals 1,200 days. Again, this is all a repeat of what we've done a few times now. Now to work the adsorption into it, KD equals KOC times FOC. It looks like for benzene, we're going to use the KOC of 83 liters per kilogram. I've also seen 58 for that number recently, but you can look it up. And the FOC of this particular soil is 0.001, so 0.1%. So that gives me a KD of 0.083, and it does have units, something like liters per kilogram. So the retardation factor can be calculated from that. The retardation factor is 1 plus the bulk density over the porosity. Looks like the bulk density is 1.5 grams per milliliter or kilograms per liter over the porosity of 0.24 times the KD, 0.083 liters per kilogram. Again, this is the same thing as kilograms per liter. And that equals 1.52. And that's dimensionless. So the velocity of the chemical, it was 0.75 feet per day just from Darcy's law. Now it's going slower than that over 1.52. And so it's going 0.49 feet per day. So the groundwater travel time, just to write it down here again, was 1,200 days. Now we have 900 feet divided by 0.49 feet per day, and that equals 1,823 days. Or we could say it's 1,200 days times 1.52 equals 1,822 days, or 1,823 days equals 5 years. So the water is going through, and a conservative tracer like chloride would go through in like 1,200 days, less than, what's that, 3-something years. This is going to take 5 years to get there. And we showed these before in the dispersion video, but you can see how that the CTET is moving this fast. The PCE is slower, so it didn't get as far because it's more retarded. And in the same time, the chloride is out there. So this is, by the way, what is this? This is gone 50-some meters, and this has gone 20-some meters, so a little less than half. So R equals about 2. The PCE is gone like 1/5 of that. So the R equals about 5 for the PCE, about 2 for the CTET. Again, the chloride is conservative, so it has a retardation factor of 1. It's not slowed down. Looking at our breakthrough curves, so we have some dispersion here. This is for a continuous source, so it's going to go up to 1. C0 equals 1. This is conservative, or R equals 1. And you can see that at 1,200 days, that comes through at 0.05. This blue one comes through at 3,600. So that is a retardation factor of 3. So it's 3 times the Darcy's law time. And this one looks like it's at 1.5. That's for a continuous source. And you notice these all have the same dispersion coefficient. It's spread out a little more because it takes more time to get there. For a pulse source or a slug source, the purple one again is a retardation factor of 1, which is conservative. It's not retarded. This is R equals 1.5, and this is R equals 3. So it comes through later. It's also spread out more because it took more time to get there. This is 1,200 days. This one comes through at 1.5, so 1,800 days. And this one is 3,600 days. It's not exactly at the peak. The retardation factor is not exactly at the peak of those. It kind of depends on the width of the pulse or how much it goes through. For this one, for continuous source, it comes through at C equals C0 equal to the retardation factor, or equal to the retardation factor times the time of the conservative one. This one, it's somewhere in there, but it's not, the peak is not exactly at the retardation factor. Here's another one. A slug input or pulse input is put into an aquifer. By Darcy's law, it takes 1,200 days to get to well A. At 900 days, by Darcy's law, in a conservative chemical with no retardation factor, so we'd say R equals 1, that would be at 3/4 of the way. And it does have some dispersion. With a retardation factor of 3, so this one's 3/4 of the way along there at that time. So that's halfway, maybe 1/4 right there. R equals 3, and it's 1/4 of the way there. A little smaller plume. It's same mass, but it's not spread out as much because it hasn't gone that far yet. So see, these are 2 different chemicals, one not adsorbed, not retarded, one adsorbed, retarded at the same time. So that would be like these guys up here, where one's out ahead of the other. Now let's look at it at a couple different times. So we're going to look at 2 different plumes. One is unretarded, or retardation factor of 1, at a time of 400 and 800 days. So Again, this is the same one we've been working with. It takes 1,200 days to get there. So at 400 days, it's about a third. 800 days, it's about 2/3 of the way there. So the plume is spreading out more as it goes. So it's a little bigger there. So this is R equals 1 at 800 days. This one is R equals 1 at 400 days. If it has a retardation factor of 2, it's going to be half as far. For the later one, 800 days, maybe it's about there. I don't know if I did the scale real great on my first one. And then for the earlier one, for the 400 days, it's going to be about there. The 800 days is going to be about halfway of the other one, about there. So this is something like that. So this is R equals 2 at 800 days, and this is R equals 2 at 400 days. Let's do a continuous source. So it's starting here. This is what it looks like at time 0. Same example we've been doing. It takes 1,200 days to get there by Darcy's law. Now we're going to say the retardation factor for toluene is 2, and we're going to look at the concentration contours. So if it's 10 milligrams per liter at the source, then the C over C0 of 0.5 or 5 milligrams per liter is going to be, all right, so what time are we? We're at 800 days. So by Darcy's law, it'd be 2/3 of the way there. We have a retardation factor of 2, so we're actually going to be half of that 2/3 on the way there. So 1/3 there. And so that's about where our 5 milligram per liter contour is going to be. So I put my contour out like that. And then out ahead of that, it's going to be lower. So maybe I'll do 3 and 1. And then I'll do a 7 and 9 behind it. And again, if I plotted C versus distance, it would be 10 at the source and then drop off with a curve kind of like that. We'll do one more video with all these plumes and breakthrough curves, and I'll talk through the homework. But the thing to get from this lecture is the effects of the retardation factor, how it slows it down, and what that looks like, and knowing that we can calculate the retardation factor from the properties of the chemical and the properties of the soil expressed in the distribution coefficient, absorption coefficient, R equals 1 plus rho B, bulk density, over the porosity times KD. All right.